Oh, the pain. Oh, the pain. Who's sending me text messages? I'm not going to do number 4, Sam. You got yours in too late. Sorry, dude. Besides, number 4. 4. It was enhanced with extra feedback. How hard could it be? Oh, we did that last class period. Yeah, I've already done it once. I'm good. I don't feel like doing it again. I'll put it out here in case we make it to that one. But we talked about that one in 6th period last week. That doesn't help you at all. But I'm just saying. Alex brought it up. Something about the stupid ropes having weight. Right? Alex is sitting right in front of me right now. I just noticed. I'm sorry, class at home. We're having a staring contest. He's looked away and blinked. He is horrible at this. He's going to lose. Aren't you, Alex? You can feel him drying out right now, can't you? You know what Sam's saying right now is that we could have been doing number 4, but instead you're having some kind of stupid power trip with Alex. I'm beginning to worry that Alex might win right now because my eyes are drying out. Come on, Alex, blink first. Fine, we're done. I blinked first, mostly because if I don't, I only have like 3 minutes with Max as it is. And if I don't get the stuff going when Max has like got any sense of attention, he'll be out the door in a few seconds and doing something that will probably annoy the crap out of me. So let's get focused here. Number 6. Teen. Golly, really? This one? This one. All right. There's absolutely no reason why a problem like this couldn't be on tomorrow's test. Quiz. Tomorrow's a quiz. Maybe today's a quiz. Yeah, if I hurry and get through all of these, today could be the quiz. And then Alex could really, really, really show me what he's good at. And then Max will be happy because he gets to do something. This will be a good day. All right, so not sure why this problem has caused you guys a little bit of consternation. Maybe you can tell me why it's hard. I guess not. So what's so hard about it? I never think of it as a system as a whole. I take it one box at a time, just like Newton's laws tell me to. So I think if I pull the bottom box out, the top box will move to the left. Does that seem not like what's going to happen? Okay. And so I'm going to make this direction the positive direction. That good too? So if box 1 moves to the right, let's make this box 1 and this box 2. So if box 2 moves to the right, box 1 moves to the left. But they both have to have the same acceleration. They're connected by a string. Fair? All right. So box 1. I'm thinking box 1 is experiencing one force to the left, tension. One force to the right, friction. Because they tell me that there's a coefficient of kinetic friction between the two boxes. It's going to experience an upward force, which I'm going to call N1 because it's the normal force from box 1. And it's going to experience weight downwards, M1G. Any questions about these? They are unbalanced. So net force equals MA. I'm thinking tension minus friction equals M1A. Let's label this friction 1 because there's going to be some other forces of friction soon. And let's see, net force in the y direction equals 0. So N1 equals M1G. There, I have exhausted Newton's laws on the first box. I can do nothing else. I might be able to do some substitution for friction, but this is what Newton's laws would give me. Any question about that? All right, because you guys said I have trouble thinking of it as a system. I have not yet thought of it as a system. I've thought of it as one box, and the forces acting upon the one box. I will now think of it as another box, and the forces acting upon the other box. So, box 2, it's experiencing a force to the right. Why? Because in the picture, there's a big F pointing to the right. There's also going to be tension to the left. Why? Because there's a string connected to the left side of the box. Questions yet? The T is probably bigger in that it's got to be at least the same size as the T that I drew on the other box. Why? Because they have to be the same size force, Newton's third law. But there's also going to be a frictional force to the left. I'm going to call it F1 because it comes from the fact that there is a downwards normal force 1, acting on the box. This is the frictional force between box 1 and box 2. By Newton's third law, it has to act to the left since it acts to the right on the other box. But more importantly, it has to act to the left because it's sliding to the box 1 is sliding to the left on top of box 1. Friction's trying to prevent it from doing so. There it is. Now, unfortunately, there's also another frictional force, F2. Why? Because there's another normal force acting on that box, N2, between the ground and the box. And there's a coefficient of friction between the ground and the box. And this is M2G. There we go. Those are all the forces acting on box 2. So, again, assembling the idea that I'm only thinking of one box at a time, let's look at this box. Net force equals M2A. This will be in the x direction, and I think there's a variety of forces acting in the x direction. I've got the applied force minus friction 1 minus friction 2 minus tension equals M2A. Questions about that? Oh, goody. So after that, I've got N2 minus N1 minus M2G equals 0. Net force in the y direction. That's it. I've applied Newton's laws. Newton's laws has produced for me 4 relationships. These 4 relationships hopefully can be used to answer the questions on this problem, but that's what it can do. It can give me 4 relationships. So I've exhausted my use of Newton's laws. It's now time to figure out if I can get the answer to the problem, which is what is the acceleration of the system. At this point, I'm probably going to have to use the fact that friction equals mu times the normal force. I think that's what's going to happen next. Any question about that? All right, so let's do a little bit of combining. Let's combine these 2 things together using this. And I will get tension minus mu M1G equals M1A. Anybody have any question about where that came from? All righty. Let's combine these 2 using the same idea. It's going to be a little more complicated, though. So before I have to answer some question from one of you, N2 is N1 minus plus M2G, which means N2 equals M1G plus M2G. Just taking that and doing some substitution. Yep. What? God. So I'm not really sure what that has to do with the problem. Better? I'm done explaining. So F minus friction 1 mu M1G minus friction 2 mu M1G plus M2G minus T equals M2A. I'm done explaining my substitution. You guys should be able to do algebra. So I'm going to add these 2 things together. Equals M1 plus M2A. That's the right side. Left side, Tensions are going to cancel when I add them together, so I'll get F minus mu M1G minus mu M1G plus M2G minus mu M1G. Done. Get your answer. You guys have everything you need. I've done all the substitution in the algebra I could possibly enjoy, and that's the answer. There's some simplification to be done, and I find it interesting. So I'm willing to at least do this. I find it interesting that a 3 comes out of that. That for whatever reason, it's 3 times that force. Probably has to do with the fact that the relative speeds between the two of those objects is actually twice as big because of the fact that they're both moving. That's probably why we have this compounded frictional issue. But hey, you just have to solve for A. I don't know what your values were. Everybody had different numbers, I'm sure. I'd be happy to go further into this problem, but I think this is all you had to do. Now, if it were me, because my big head was in the way and I want to be a jerk, I don't think there's anything wrong with suggesting we take it up a notch. Why not? Who said it had to be attached to a wall? What if it's attached to another block? This is because I lost the staring contest earlier. And because I just don't think people are asking enough questions. And when they do, they only ask questions about algebra, and I don't like that. Yep. Well, this would be a 4-body problem with one of the bodies not having any mass. Now, you could actually just take and say that it's a 3-body problem and make this a part of this block, to which you would have a third diagram with tension, tension, friction, normal, M3G. The problem, and this is why this one would be actually ultra hard, is you have no idea how this block moves, the big one moves, with respect to anything else in the system. It would be a challenging question. But I'm okay with the challenging question. Josh, you don't want the answer to that. You don't want the answer to that because I'm not sure you can explain to me the other problem. And this one I don't think is within your purview. No, I'm not trying to be negative. I'm saying I don't think that this problem is worth us going into. It would be interesting. I would augment this problem a small amount to make it something that you guys could actually do. Right now, because of the acceleration being relative, meaning the acceleration between M2, M1, and M3 not being something you know, makes this problem very challenging. I would probably throw you a bone and indicate or give you a piece of information that's not being stated here. But it's a neat idea. All right, next, because I don't remember what they were, and I've made them too small to see. I put this big block in the way. Oh, number 9. I don't remember what number 9 is. Number 9. The rope one. The rope one. Well, I'm going to use this as a teachable moment since I have to do the rope one for the 3rd time today. There's the rope. We want the tension in the rope at point P, a distance y above the bottom of the rope. And we are told that the rope is L long and has mass equal to m. If I were trying to use this as a teachable moment, one of the things I would probably encourage you guys to remember is your chemistry. Luckily, I have some chemists in the room who can remind me about density, right? Of course, everybody who's an E&M knows what these three symbols represent. Alex, what do these three symbols represent? That's right. Linear density is mass per unit length. So it'd be kilograms per meter. Areal density, which is not like from the sky, but it's like about an area or a surface, is mass per unit area and be kilograms per meter squared. And volumetric density is the one you learned about in chemistry, and it's the mass per volume. These were physical properties. Anybody who's played guitar or is in orchestra knows about linear density. That's how the strings are set up in any stringed instrument, using the density as a way of adding inertia to the string so it plays a different note. Linear density is a way of doing this problem because if we think about the fact that the string has perhaps uniform density, then it's likely that we could take whatever the linear density is and multiply by some length of string, and this would give us the mass of this length. I'm using X here as a placeholder to indicate some length of string. Now, to figure out lambda, I need to take and get the mass of the string and divide by its whole length, which in this case is m over L. That is the linear density of the string. More importantly, at point P, the net force is 0 because that point on the string isn't accelerating in any direction. So I could say that at point P, there's an upward force, T, and a downward force, weight. And this would be the weight of the string beneath point P, which would have to be the mass of the string beneath point P times G, which in this case would be lambda times Y times G, which, based on what I've been given, is m over L times Y times G. This would have to be the tension. More importantly, switch it around a little bit. I would hope that you would have figured out that it's just the percentage of rope beneath you. That's what Y over L is. When there's 0 rope beneath you, you're at the bottom of the rope, there's no tension. When you're at the top of the rope, L, the entire rope's beneath you. Yeah, that's it. That's number whatever it was. Questions about it? Interestingly enough, I bet the density of the rope isn't uniform from the top to the bottom. I bet the density is less at the top and is more at the bottom because I bet the density of the rope is related to the tension. Because the more you pull on something, the more it would stretch, which would make this actually a quite interesting question if you really wanted to look into it. But that's probably a conversation for people who understand calculus, because you would have tension as a function of position on the rope, which is also a function of density of the rope. That would be an interesting question, but maybe too much for this class. All right, so I have to do number 11 next. We have to hurry because we're boring Shreyas. He's got his head down and is asleep. So it's like how I feel when I'm writing letters of recommendation. I'm just bored. I'm going to put my head down. Oh, wow. This looks familiar. All right. So there's a box on a box on a box. Is that what I'm seeing here? Or just two boxes? Just two boxes. And a string. M1, M2. What else do we know? Coefficient of static friction of point something or other between the two blocks. So coefficient of static friction, that rings a bell in my head. I better put this down so I don't forget it's an inequality because I might forget otherwise. And the coefficient of kinetic friction between the lower block and the floor is something else. Uh-oh. Uh-oh. Kinetic friction now down there. All right. And force F causes both blocks to cross a distance starting from rest. Okay, I don't care about any of that because none of that has to do with force. What is the least amount of time in which this motion can be completed without the top block sliding on the lower block? Least amount of time means fastest moving blocks, which means highest acceleration. So highest acceleration sounds like what is the biggest force I can apply? So I think I am looking for this value. But really I'm not, because they want time. So what I really want is this value, the max acceleration I can actually have in the system. So at some point or another, I'm going to see probably A has to be less than or equal to something. I'm saying it this way because if I want A to be a max, some function here, I'm saying that the value has to be less than or equal, but not greater than this. That's a maximum. So eventually that's where I should get. I should get something where A is less than or equal to something. I'm throwing this out there because I think you guys don't really know that. I think max means less than or equal to, and I think minimum means greater than or equal to. And I think you should know that. If you don't, you haven't really been paying enough attention to the nuance. Well, this one's hard, but ultimately I just want an acceleration. After that, it's a motion problem. I think you can all agree I don't want to do the motion problem part of this because that's beneath, well, it's beneath you. I mean, it's on your next test. So if I have to, I will. But I'm going to start the problem the way I think the problem should be started, which is free body diagram, top mass first, F this way, and friction this way, and weight this way, and normal force this way. I'm going to call that normal force 1, and this friction force 1. And I'm going to state that the net force is equal to M1A. Questions? Okie doke. Next box. Well, I'm thinking F1 this way, F2 that way, N1 this way, M2G that way, and N2 this way. Net force equals M2A. Any questions about that? Yes, sir?
Wouldn't F2 be greater than F1?
I don't know. I don't think so, because I think box 2 is going to accelerate to the right.
Okay.
And I think we want to maintain a situation where both boxes are together. So maybe I do know that F1 has to be greater than F2. Right? It's the only way the system accelerates to the right. So it must be. We can find out later, but I think it would have to be.
Okay.
Does that make sense?
Yeah.
So I'm not trying to be flip about it, although I am feeling kind of like a jerk right now in trying to, in responding this way, and I shouldn't. Talking it out to you, what I'm trying to indicate is that the only way block 2 can accelerate to the right is if the unbalanced force is to the right on block 2. So unless there's another force acting in the system that acts to the right, F1 would have to be greater than F2.
Yeah, no, that seems obvious. Like now that you say it, it's just like I'm struggling with like when there's friction between the table and friction between the block. I'm struggling seeing that as just like on the block and not just there's a friction up here and friction down here. You know?
Yes, and I can understand that too. The fact that we have two surfaces with potentially, that potentially create a normal force, that's why we have the two frictions, but they do act on two different surfaces.
Yeah.
Now, another piece of this is we don't have to do the problem this way. It is quite reasonable that we could have done the problem a little different than this. Meaning we could have just looked and found out what is an expression for the acceleration of the system in terms of this applied force and treat it like a system. We wouldn't know whether we had the right answer or not, but we would at least have a place where we had a function of the acceleration in terms of this applied force and the weights of the system, meaning F minus friction for the system would have to equal M1 plus M2A. Now, this has to be true even now. This is eliminating that internal force, but by doing the problem this way, we don't know what the limits are. And so this is why we can't really do it this way, at least not in the onset. We could say that this is our acceleration, sure. In fact, that's going to happen here in a minute, but it doesn't provide us our opportunity for our limiting value, which we'll have to get in a minute.
Mr. Shelton?
Yes.
Why is there a normal force downwards on block 2?
Because block 1 is sitting on top of it. Block 1 is pushing down on block 2.
Okay, thank you.
You're welcome. So let's go forward with this and see how we're going to proceed. I'm trying not to break the mold of the way we've been approaching all of these problems today, because I've had a few people complain is the wrong word, empathize that they're having difficulty with these problems. So I'm trying desperately to do every single problem exactly the same way, even if it's not the most efficient way. Does that make sense to all of you? So I've drawn my free body diagrams. I've set my problem up. So I'm going to go further now and actually employ what's necessary to solve this problem, which is looking at all the forces that act in the system and satisfying Newton's law. So here I'm going to have the applied force minus the frictional force equals M1A. And I also know that N1 equals M1G, net force in the Y direction. Now, here's where I run into some difficulties. F1 has to be less than equal to mu S times N1. There's where my condition is. And so I'm going to have to be careful about dealing with the condition. I might not be able to deal with it right now. I might have to come back to deal with it. So I'm going to keep going because there's nothing else I can do here. Looking at block 2, I'm going to have F1 minus F2 equals M2A. Now, F1 is also, again, is our limiting force. But we don't know what A is. But I do know that F2, Mr. Shelton, sorry, I screwed up. I do know that F2 is going to be related to N2. So I can go that route and say N2 equals N1 plus M2G, or N2 equals M1 plus M2 times G. Now, the reason this is important is because I know that F2 is equal to mu times the normal force. So I can do that substitution right now. So I'm going to make all this a little bit, maybe I'm not going to do that. I'm hoping there, make all this a little bit smaller, put her over there for a minute. And just remind us that F2 is going to be equal to mu k m1 plus m2 times g. Okay? Any problems yet? Alrighty, so I have F1 minus mu k m1 plus m2g equals m2a. That looks good. I like that. And I have, I don't know what to do next. This is one of my work function equations, and this is another one of them. I don't need the applied force. I need the acceleration. So I'm thinking, since this is my limiting part of the problem, that I think I have everything I need to figure out my limits. Meaning I have an expression for F1. It equals mu k m1 plus m2 times g. That should be parenthesis there. Equals m2, I'm sorry, not equals, plus m2a. This is all F1. And this is N1. I think I can substitute into F1 is less than or equal to mu s times N1. Again, I use Newton's laws to produce this function, and this function. And I'm just seeing how I can relate them together. This does not give me the force that I can use to apply to the system, but it gives me the acceleration, and that's all I need to figure out what the time it takes for it to move. So I'm going to skip finding out what the applied force is and go straight to finding out the acceleration by saying mu k m1 plus m2 times g plus m2a has to be less than or equal to mu s times m1g. There it is. Now I can solve for A. Luckily for me, it looks like when I solve for A, I will be getting a maximum because A will be on the right side of the comparison symbol. So let's go. A is less than or equal to mu s m1g minus mu k m1 plus m2 g all over m2. That is hideous looking. But I think it's right. In fact, interestingly enough, I can factor out the G, and everything in there is unitless because I have something in kilograms on the top and kilograms on the bottom. So I get something that is, I hope, a percentage of G. And I'm pretty sure it will be. Now, let's answer Jack's question, because I think it's right here. There's a negative sign here. There's the potential that this does not work. The potential where the forces won't allow this to accelerate. And it has to do with this. If the frictional force is too big, if the kinetic friction at the surface is too big, the static friction won't be enough to pull it to the left. And that's the condition. Mu k times the two masses. Think about it. That's all the normal force and the percentage of normal force that makes friction at the surface. If that side is bigger than just the part that makes the static friction, this doesn't make any sense. I can't have a negative acceleration. I can get zero for a possibility, and that's the point at which it just won't work, is when that max acceleration is zero. Aside from that, this is good. This is it. That's the answer. That's whatever that is the acceleration. I'm confident in it. I like doing it this way. And we answer everybody's question because I guess all of you had different what? Different coefficients, it looks like. Is there more to this problem? Nope, that's it. Any questions about it? There is another way you could have approached this problem. I don't think it was easier, but there's another way you could have approached this problem. At least that I can think of. Yes, sir.
I can't find my word, but last night when I was doing this, I did it like as a system as a whole,
Uh-huh.
and I didn't do it this method. But when I was trying to solve it, I had to look it up because when I was solving for the acceleration and I was using a normal force, I used M2 plus M1.
Okay.
For some reason, when I looked it up, and I kept getting the wrong answer, so I looked it up, and they used M2, just M2, not M1 in there, like M2 plus M1 is their normal force, while they were calculating the friction between M2 and then the floor.
Well, we get that here. Right, that's where that frictional comes in. That's the M1 plus M2.
That's what I was trying. That's what I was trying to say because it's supposed to be M1 plus M2, but they only used M2 for some reason, and I put that answer in for mine, and I got it right. I used just M2, and I got it right.
Couldn't tell you why that would be true. I don't see that here.
I don't know. It was just I got that right when I put just M2 in there.
Yeah, I'd have to see what you did.
Okay, I'll bring my work. I don't have it right now. So.
They don't give me a solution. So I'd have to, I'd have to put stuff in there. And this isn't the answer either. You guys know that too, right? You have to do a motion equation after this to get the answer. I will say, if you did this for the system, net force equals M1 plus M2A, and said that you only had friction minus, the applied force minus friction. If you did something like this, which you could have done by eliminating this equation and this equation together, you'd have the acceleration in terms of the applied force. You would still have to eliminate the applied force. It was not given. All right, I don't see the applied force here. So you would still have to have found a way to eliminate that force. All right, I'm done. Next question. I have no idea which one we just did. 11. So next is 13. How you doing, Alex? Did you get this question right? Probably. Don't even know, huh? All right. All right, so this has got a whole bunch of pulleys. So there's this big pulley. There's this little pulley. There's this one connected like so, and this one connected and then there's a box down here. So now I got to string it all up. So this string is connected to this fixed point. This string is connected to the side there. This string is connected down, and there's a string here. And this is T1, T2, T3, T5. Oh, and then there's a one above this. T4. All right. Now, what do they want? Find the tensions T1 to T5 and the magnitude of the force F. All right, so this is M. So T1 equals mg. Question about that? All right. T2 equals T3, which equals half of T1. Any question about that? Okay. That also equals T5. Any question about that?
How do you know that it's equal to T5?
They're all one string. It's all, this is all one continuous string. So it must have the same tension throughout all of it unless the pulleys have inertia. And even in this case, the pulleys having inertia isn't enough because they're not accelerating.
Okay.
That clearly didn't answer your question.
No, I get it. I get it.
Okay. So at this point, T4 is all that's left, and T4 has to be the sum of T2 plus T3 plus T5. And since each of them is equal to half of T1, T4 has to be equal to 3/2 T1, which has to be 3/2 mg. Boom.
Mr. Shelton,
Yep.
why does T1 or the mass hanging not factor into T4 since T4 is like holding up the whole system?
Well, the simple answer is to state that it does, but it doesn't do it directly. The mass is not attached to this rope. This rope is not attached to the mass, but it's attached to things that are then attached to the mass. So all I can say about T4 is that at this point right here, if I use that as the pulley, that one has T4 acting up and T2, T3, and T5 acting down. And at that point, the net force still has to be 0.
Okay, gotcha. That makes sense.
Okay. I find it a little interesting that the ceiling has to provide 50% more force in order to maintain the weight of just the block sitting there. Don't you find that weird? And if you don't, well, then I don't want you designing any crane that's near me. Yep. Well, then I'd have to put all their masses into all this. So starting here, so T2 and T3 would be bigger than what we said because it'd have to accommodate the pulley's mass. T5 would still be equal to T2 and T3. But then when I went to go T4, I would have to add the mass of that pulley when dealing with T4. So T4 would be greater again. And it'd be greater twice because T2 and T3 both are greater than they were before. Okay? James?
So in this problem, it wasn't accelerating, right?
It was not accelerating.
How would it be different if we applied a force to T5 that caused the mass to accelerate upwards?
I would think that all the tensions would be greater.
Okay.
They'd all have to be. I mean, starting with T1, for the weight to accelerate upwards, T1 has to be greater than the weight. Therefore, T2 and T3, although half of T1, still have to be greater than the weight of mg. And then T5 being connected to T2 and T3, it will be greater. And therefore, T4 is going to have to increase its amount of tension to deal with the fact that the net mass of the system is moving upwards or accelerating upwards. It would have to support that.
So in that scenario, you said T2 and T3 would both have to be greater while still being half of T1. Would each individual tension have to be greater than the mass, or would it be the sum of the tensions greater than the mass? Okay.
I mean, this would still be 0. We're saying the pulley is massless, so. All right. I think there's still one more left, right? Maybe. I don't even remember. It's so long ago. Well, I know that'll make you happy. So number 14 is next. Oh, this is testable, sure. This has been on the exam. This has been on the AP1 exam. By the way, this is the same. If the table is frictionless, this is just an Atwood machine with extra inertia. But generally, if I'm thinking APC, I'm thinking that I'm going to add friction to the table. That would make it an APC level question. Bye. I will finish this question though, because I don't know who asked it. But if you have to go, you have to go. So I've got this as M1, M2, and M3. And they do say that there's a coefficient of kinetic friction of mu between the block and the table. And they want the acceleration of the 2 kilogram block. I'm thinking that's whatever the acceleration of the system is. So
No, it's not. No, it's not.
positive direction. Look, I think it's just going to be you guys at home. If you don't want to stay, you don't have to, but I don't know who asked this, so I'm going to finish. And that way, you know, it'll be on the video. So I'm going to state that this is M3G and this is tension. I'll call this tension 3. And then block 2 is going to have tension 3, tension 2, M2G, normal, friction. And then block 1 is going to have tension 2, M1G. We good? All right, so bye. So if I look at all of them together, I'm just going to do the parts that are accelerating. So this one's going to be M3G minus T3 equals M3A. And box 2 is going to be T3 minus T2 minus friction equals M2A. And M1 is going to be T2 minus M1G equals M1A. Any question about that? All right. This is the nucleus of this problem. Plug everything into there, you'll get the right answer. I'm going to make one change. Friction is mu M2G. And now I'm just going to add all 3 equations together. And I will get M3G minus mu M2G minus M1G equals M1 plus M2 plus M3 times A. And that's it. That's how it's done. Any questions? How are you guys? I'd study tonight. Body language in the room was a little weak all day today, so I'm feeling a little bit like making sure that I know you guys know what's up. And since it's just the 3 of us, I would consider that the last time I did that was the cable pulling the block on top of the other block. Remember that? People didn't do particularly well, and I was nice enough not to include that. I am not going to be that person tomorrow. Not with the kind of deal, not with what I had to deal with today in front of me. So I would encourage you to know this stuff. All righty.
Mr.
I'm not
Shelton.
gonna be mean, but I'm gonna be thorough tomorrow. Go ahead.
So I know you've mentioned like how adding friction to the table will change the problem, but how would it, like, how does it change the problem? What does it
Well,
add to it?
Friction's on this right here. This wouldn't be here if it wasn't for the friction on the table.
Okay.
If there's no friction on the table, there'd be no external force on the system. So I would just have the weight of the 2 blocks hanging down and their combined inertia.
Okay. And then I saw on Canvas, I was looking at the agenda for the week, and it said, so it's a unit test. So is it covering all of Newton's laws?
All of Newton's laws. There'll be circular motion, there'll be friction, there'll be multi-body problems, the works.
So will it have like the stuff from last test too that dealt with Newton's problems?
Most
Or just-
definitely.
Yes.
Yeah. I mean, because
Okay.
that stuff is here. I mean, all
Yeah.
of the single body parts of these are the stuff from the first test.
Okay. And what chapter is this in our textbook so I could do some extra practice?
Well, these problems are from chapter 2.
Okay.
No, I'm sorry, chapter 7. It says problem 7.38, so that must be chapter 7.
Thank you.
You're welcome. All right, guys, I'll see you all tomorrow.
Have a nice day, Mr.
Bye,
Sheldon.
Mr. Shelton. Have a nice night.
Bye-bye.